Hi, my name is Daniel Mendoza. I am student in engineering from Universidad Estatal Francisco José de Caldas. I work as a software developer in Bogota, Colombia. I send greetings to all attendees of the third International Congress on Economic, Social Science and Information Management. I will explain an investigation entitled Communication Infrastructure for Monitoring Heart Rate of Patients on the Cloud Using IoT Devices. The program for this conference is as follows. Background on telemonitoring and its impact on health. A general view where I explain the problems solved by telemonitoring systems and their impact on health problems on Colombia. Processes that extending transmission times in these telemedicine systems, as in any other information systems, the processes for performing a functionality may experience delays and blockages. Optimist solutions. We propose a communication infrastructure model focused on a telemonitoring system solving many of the common problems of processes blockages. Case studies assessing real-time data transmission processing times with sensors. And we evaluated the processing times of the proposed model for two specific cases. Finally, the results analysis and conclusions. Telemonitoring is a specialty of telemedicine that has enabled to the monitoring and management of information from patients treated remotely, such as remote monitoring of a person's physiological and biometric parameters. In addition, it has become in a strategy to improve disease management. In turn, it involves several benefits, including the effects of patients' conditions and clinical effectiveness, such as the decrease in emergency care and hospital admissions. In Colombia, for example, there are many problems to treat patients directly due to the geographical distribution and few coverage of health specialists. And not only in Colombia, also in several Latin American countries, and also where there is a large rural populations. Then arise telemonitoring systems to counter these problems. Although there are very good solutions, but usually have very high prices and difficult to maintain because they need very qualified personnel for the systems. That is why we also set a stage with open source and low price technologies. These are the common problems in these and other information systems. When information is transmitted in real time and also the information is stored, it sacrifices a lot of time. That is, they become processes dependent on each other. In addition, when you want to monitor many patients at the same time, if the infrastructure is not ready, you may experience concurrency problems, and if we add to it, that is not possible to scale technologically, two purposes of telemonitoring cannot be fulfilled. Then the problems mentioned above were addressed by implementing the following strategies. Delegate the insertion process to a distribute task queue system, mechanisms to distribute work through threads or matchings. In this way, it is still transmit, and in the background information is stored. An exchange of distribute message focused on the operation in real time, parallel computing, support high concurrency. With this, we shorten the time for the information to be ready to consult, and through parallel computing, the infrastructure can support scalability and high concurrency. This is proposed in communication infrastructure model. And IoT devices propose large amount of information, not a structure. Therefore, so we use a non-relational database as MongoDB, used in database management designs that require high performance in telemedicine. Starting with the patient, it will have a sensor that communicates wirelessly to a receiver through the GPIO port with the Raspberry Pi. The latter has a data capture interface. It serializes the data in JSON format to be sent via the WebSocket protocol to the server. The server offers a bidirectional WebSocket channel for real time and unidirectional HTTP channel for data query. Tornado receives information from the patient. The insertion in MongoDB is delegated to an asynchronous task queue, and finally, it transmits the information to a receiver. This task queue performs the processes independently, that is, without a process having to wait for another to finish to be executed. The receiver communicates with the server using WebSocket and HTTP depending on its activity. In order for the transmission of vital signs not be blocked by the information storage, this last task is delegated to the task queue. As a result, asynchronously the data is transmitted immediately without having to wait for the storage process to finish, thus establishing parallel processes in order to reduce the data transmission time. We propose two case studies to evaluate both the time required for a Raspberry Pi serve and the asynchronous queue for 1 and 2 sensors. The objective is to determine if the time difference is too much. We can see the Raspberry Pi, the sensor, and the person who will use this sensor. The case is described in this slide. The program made received the captured signals from the heart movements. In addition, it established the persistent bidirectional connection with the server. After receiving each signals, it serializes the data in JSON format and sends it to the server. The JSON message is then deserialized and the message is sent to all connected clients. Finally, the same message is sent to the distribute task queue for insertion into the database. In case 2, we add a sensor that measures the temperature and humidity of the environment. In this case, with the same variables, it is sought to determine the difference with the number of inputs and the number of sensors. Here we can see the results of the time for each processes. At a glance, we can notice that for a server processing, times and celerity is the asynchronous queue, the behaviors are very similar, where if we notice a difference is in the behavior of the Raspberry Pi. This means that the difference between the static cases influenced more in Raspberry Pi than in the server. And in results analysis, the difference is not very big, as we observed in the graph. Although the JSON document is larger in case 2, in addition to the cardiac signals contain the temperature and humidity of the environment. The server and the synchronous queue were faster in this case. However, the difference is not very big. On the server, done not very many times to process more than one entry. This means that can handle many transactions. And at the server level, it was 0.08% faster in case 2, while the asynchronous queue was 2.52% faster. The critical part of the infrastructure is the Raspberry Pi, and this is where many efforts must be made to optimize transmission times. We can finally observe the weight difference of the two case studies. In case 2, since it contains more data to receive from the sensors, the processing times will therefore be higher. Total processing time between the sensor components and the server was 14.48% faster, handling only the cardiac signals. Final conclusions. First conclusion about console patient information. Infrastructure proposed is ideal for the capture and processing of cardiac movements. It also allows to store each of the capture movements and send them in real time to a receiver. And parallel processing. Queuing of asynchronous tasks was fundamental because data storage and the transmission processes in real time are performed in parallel. And future work, a central unit can manage a greater number of sensors without increasing the time involved in these processes. Thank you. And for any questions, you can read me an email and me and Paulo Alonso Gaona and me, collaborators in this project, engineering research groups in Colombia, and the founding Universidad Estatal Francisco José de Caldas. Thanks for all.